All right, it's 1 o'clock, so we're going to get started. Hello, everyone. Welcome again to this week's lecture for the MTV Nuclear Engineering Summer School. Before we get things started properly, just as a quick reminder for everyone, regarding the question and answers for today's talk, feel free to put them over in the Q&A section, and we'll go over them at the very end of the lecture today. Just as a reminder, please keep questions only relevant to the subject of the talk, and any other miscellaneous questions, feel free to reach out to the regular email that we use. So, with that out of the way, today's lecture is going to be given by Colton Graham. He's a PhD student here at the University of Michigan in Professor Jovanovich's research group. He's going to be talking today about some more neutron imaging today. So, without further ado, Colton, go ahead. The floor is yours.
Hey, thanks, Ricardo. So good afternoon, everyone. I'm Colton Graham. I'm a fourth-year PhD student working with Professor Jovanovic, and today I'm talking about imaging plates for fast neutron imaging. So I'm sure most of you all know what the National Ignition Facility is, but in case anyone doesn't, NIF is a world-leading fusion research center based on inertial confinement fusion, which is an alternative to the more commonly used magnetic confinement fusion. In ICF, external lasers are used to put pressure on a combined target of deuterium and tritium. That then condenses the target, which induces fusion, which can be used as a source of fusion energy. Now, NIF 2022 was the first fusion center in the world in order to be able to achieve what's called ignition, which means that more energy was put out of that system then was put directly into the fusion target. Specifically, they were able to get 3 millijoules of energy out of their fusion target, as opposed to the 2 millijoules of laser energy that were put directly on the target. Now, this does ignore the fact that only about 10 to 20% of the total laser energy ends up on the capsule, and a great deal more energy is needed at earlier stages of the total process. But still, the NIF is the first system in the world in order to be able to achieve ignition, which is an important step on the process towards fusion energy. Now, one of the key breakthroughs in NIF's experimental work was the introduction and use of diagnostic tools. There's over 120 diagnostic systems and over 650 diagnostic channels that are present on the NIF, which provide information both to the NIF physicists as well as to external users, as NIF is a user facility. And there's a number of different diagnostic systems on NIF, which fall into 3 major categories. There's the optical diagnostics, which measure the power, spectrum, and angular distribution of light produced in the fusion event, and that allows you to determine the total energy balance of the experiment. There's also measurements of the X-ray emissions using particularly fast detectors, which allows you to probe the plasma matter inside of the NIF chamber, as well as nuclear diagnostics, particularly those based on neutron measurements. And that allows you to measure the neutron yield, as well as the ion temperature of the plasma, as well as image the spatial distribution of the plasma in order to get some idea of what's going on. And this information can then be fed back into NIF's design process iteratively in order to improve the quality of NIF's experiments, in order to allow for more energy to be extracted out of the system based on things like target alignment, target temperature, and target manufacturing schemes. Now, one of the most important of those diagnostics is neutron imaging, like I mentioned. And this can allow you to do things like image the fuel spot size, the fuel spot of the confinement system. And this allows you to determine things like, for example, the degree of confinement of the system, right? Relatively low degrees of confinement will allow energy to escape, which will decrease the total energy of the system. However, a higher degree of confinement keeps the plasma confined in one spot, which allows fusion to continue to go on, which results in a total greater amount of energy being released. And by taking an image of the fusion events based on neutron imaging, you can determine things like laser misalignment or how different fabrication techniques and the precision of the target fabrication impact this confinement. And particularly by taking neutron images at different uh, angles relative to the target system, you can build a 3D model of the confinement. And this gives you a lot of information to work with. And you can see an example of that on the bottom left. And then on the right here, we see an example from, not from NIF, but from the Omega experiments at University of Rochester, in which they introduce an intentional and measured degree of misalignment between the laser and target systems. And you can see how that impacts the degree of confinement of the system, right? At higher degrees of misalignment, you get this spreading out of neutron events corresponding to a spreading out of the plasma, which decreases the total degree of confinement, which decreases the amount of fusion energy that's coming out of that. So all this is information that you can extract using neutron imaging. Now, neutron imaging at NIF is based on, at the moment, is based on pinhole aperture imaging. You can see on the right here the aperture system that they use. It is a 20 centimeter thick piece of gold. You can imagine it's a very, very thick, very heavy piece of gold, where gold is selected as at the high energies of the DT fusion, 14.1 MeV. Gold has the highest total neutron cross section, which results in the highest neutron attenuation. So that neutron pinhole is placed 20 centimeters from the NIF target, and then 28 meters from that down one of the beam ports from NIF. There's a number of different neutron imaging systems. On the left here, you can see one of those, which is based on a scintillating array, which is guided through a set of optical fibers into a charged coupling device camera, a CCD camera. And that provides a highlight output, a relatively good image resolution image of the neutrons. There's also a number of other imaging systems using image plates, which we'll talk about more later. Now, more recent work on NIF has introduced the idea of using coated aperture imaging, and that can be done using hundreds of microns thick tungsten targets. And that's been demonstrated in simulation, and work is ongoing in order to implement that. Now, there's a number of other applications beyond just NIF's fusion diagnostics for neutron imaging, and I want to highlight a couple of those. One is for homeland security. Neutron transmission imaging is a really effective tool for scanning cargo for contraband. That can be drugs, explosives, chemical weapons, or special nuclear material. In particular, using the total neutron and gamma ray attenuation can provide an estimate of material density, which can allow you to, say, discriminate the low Z material of drugs or explosives from the relatively high Z material of metal cargo or of a cargo container itself. Whereas the ratio of the neutron to gamma ray attenuation provides an effective Z number, which can allow you to discriminate contraband low Z cargo from other benign low Z cargo based on the Z number for each of those. And you can see a number of examples here on the right in which the R, the ratio of the attenuation of neutron and gamma rays, is measured for different Z number targets, as well as on the far right there, you can see examples of scanned images using neutron imaging. Another example is medical application. Thermal neutron radiography is a popular alternative to X-ray imaging. It's particularly advantageous for highly hydrogenous material, in which there is not a high degree of difference of the attenuation of X-rays from things that you're interested in versus things you're not interested in. For example, on the top right here, you can see an example of, on the top is measurements of a section of material with a tumor. On the top, that's neutron imaging, and on the bottom, there's X-ray imaging. And you can see a higher degree of contrast for the tumor-containing material in this sort of light white here, based on the neutron imaging as opposed to the X-ray imaging. Additionally, gadolinium can be used as a capture tracer due to its high thermal neutron capture cross-section, and this can be used for thermal neutron imaging of organs. You can see an example down here. And thermal neutron diffraction can be used as a tool for imaging of proteins or viruses. For example, on the bottom right here, you can see models based on images of the COVID-19 virus that were taken at the spallation neutron source, which is a thermal neutron beam source at Oak Ridge National Lab. So there's lots of different applications along with fusion diagnostics for neutron imaging. But image plates are generally a really useful tool for radiation imaging. They're very commonly used tools for X-ray imaging, either for medical applications or for others. You can see an example here of an image taken using X-ray imaging with an image plate as the actual imaging detector. They're also very commonly used as accelerator diagnostic tools. Image plates can be used in order to measure the beam spread and beam distribution of an accelerator, which can act as a diagnostic tool for the accelerator physicists. They're also very useful for imaging for material physics. You can see an example here of an image taken with of silver bromine microcrystals taken using image plates, as well as taken a more traditional X-ray film. And you can see that the higher image resolution of image plates is advantageous here. It gives you more information. And there's a number of things about image plates that makes them relatively appealing. As compared to more advanced systems based on, say, scintillators and CCD cameras, image plates are relatively cost effective and they're commercially available and very easy to use as compared to these systems. Now, compared to the more traditional and very common X-ray films, image plates are advantageous as they're very durable. The X-ray film is very easy to accidentally rip. They're very thin films. Image plates are also reusable as opposed to X-ray films that once you embed an image on them, you have to throw away once you're done with. But most importantly, image plates are highly linear at a high dynamic range of radiation doses. And this is particularly advantageous for NIF, which is a very intense radiation environment. So it's very important in order to have this image linearity in order to take accurate images. And you can see a couple of examples here in which image plates were exposed to a very high flux of beta radiation. And you can see the high degree of linearity as compared to X-rays. And then on the right here, you can see that's true for, as opposed to films. And then you can see here on the right, the high degree of linearity for X-ray irradiation on image plates. So these are useful in a wide range of imaging applications. Image plates are based on photostimulated luminescence as their imaging physics. Typically, image plates are constructed as a thin layer of some photostimulable phospholayer. Typically, that's based on a barium fluoride halide, where the halide is either chlorine, bromine, or iodine, with europium 2+ dopant in that. This photostimulable layer is embedded on top of a support, which is usually some piece of plastic with a magnet on the bottom, where the magnet is just useful to attach it to readout systems or to attach it to say some component of an accelerator where you're going to have the accelerator beam incident on that. Additionally, the phosphor typically has a protective layer of mylar on top of it in order to prevent any damage to the layer. Where mylar is selected as it's light transparent and can be made very thin and is waterproof. Now, the actual imaging is done via the photostimulated luminescence via PSL, wherein X-rays or some other ionizing radiation induces an electron from the europium dopant to be knocked off of that. That then interacts with the chlorine, which produces a so-called F center, which is essentially a metastable trapping of that electron in near the conduction band, where that electron can then be induced to go back to the europium via light being incident on the photostimulable layer, and then that electron, as it's going back to the valence band loses its energy via light emission, and that acts as the trapping of the imaging information in this F center. So these image plates are read out using laser scanning systems. Typically, you take the image plate and you put it inside of some laser scanning machine that can either be based on a point scan system, like the example in the top right here, in which you have a single laser beam incident on a point on the image plate. The laser is then brought across the image plate and then moved to the image plate is then moved, or the laser is moved, and then that just continues to read out like that. More modern machines will use a line scan system in which the laser is split into a line where the light emitted from each section of the line of the laser is then brought into a CCD array, and this just allows for a quicker readout of the image off of the image plate. But the point scan systems are very common. The light from this is then collected typically by either a PMT or by a CCD. And then after each usage, the image plate could then be cleared by exposing it to a really intense light. And that can be done just by putting it under a bright white light. And that intense light induces movement of the trapped electrons in the F centers down to the valence band, just clearing the image plate for its next use. Now, there's a number of different properties of image plates that I want to just introduce first off. So firstly, there's a number of different types of these image plates. The most commonly is the multi-purpose standard, or MS, image plates. These have the highest degree of sensitivity, but have the lowest image resolution. And this is, they have the highest sensitivity because they have both the thickest mylar, or they have the highest sensitivity because they have the thickest of the photostimulable layer, but they have a low resolution as this requires a high mylar layer on top of that. And you can see here in the center an example of a measurement of the total amount of light for each of the different types of image plates as a function of X-ray energy. And you can see that the MS image plates consistently have the highest sensitivity. An alternative of this is the super resolution, or SR image plates. These have a thinner photostimulable layer and a thinner mylar layer, which gives them a lowest degree of sensitivity, but gives them a higher image resolution. You can see on the right here an example of a comparison of an image between MS and SR image plates, and you can see that there's a much sharper image using this SR image plate. This does require having a higher resolution scanning system, at least a 50 micron scanning resolution system, which many systems are not because they're just designed to be used with the MS plates. One other type of plate is the tritium sensitive plates, or TR. These have no mylar shielding on them, which makes them ideal for detection of the lower energy betas from tritium emission, or makes them ideal for heavy charged particle detection, which is important in many accelerator diagnostic applications. One other type is that for thermal neutron detection, or the ND plates. These use a gadolinium doping in order to be sensitive to thermal neutrons, in order to direct thermal neutron imaging using this image plate. So the image plates are themselves sensitive to charged particles as well as to low energy photons, where low energy photon the X-ray sensitivity, or low energy gamma ray sensitivity, is based on gamma ray electron reactions happening in the image plate. And you can see on the bottom right here a measurement of the sensitivity for each of the different types of image plates for both X-rays and direct beta electrons on the image plate. And again, you get the same trend of sensitivity as previously, where we note that at really low beta energies, the TR has a much greater sensitivity due to it not having the protective mylar layer on top. These are also sensitive to alpha particles and heavy charge particles. You can see at the top there measurement of the total light output as a function of the alpha energy deposition in each of the three major types of image plates. We'll note on the table on the bottom left You can see the total amount of light output per kV of energy deposition, and you can see there is a strong quenching effect, very similar to what is observed in organic scintillators. You get a much lower degree of light output with either protons or with alpha particles. And this is due to a similar reason for organic scintillators, right? Based on crystal defects caused by the higher degree of damage from these heavier charged particles. One other important property of image plates is their fading effect. Due to thermal recombination of electrons trapped in F centers with the europium 3 plus molecules, you get just a natural fading of the image over time. And you can see on the right here a measurement of the fading after X-ray irradiation for each of the three major types of image plates. And you can see that this fading occurs quite quickly, on the order of minutes, tens of minutes. You get losses of 10, 20, 30% of your signature. And you get a higher degree of fading with the TR image plates due to the lack of mylar layer, which acts to thermally insulate, as well as to insulate from light coming onto the image plate, which can cause additional fading. So if these image plates are intrinsically sensitive to charged particles, how do we use them for neutron imaging? And the answer is that we need to use neutron to charged particle converters. Typically, that's neutron to proton converters, but there are other schemes that have been demonstrated as well. And a neutron to proton converters is based on the fast neutron elastic scattering in some hydrogenous material. And that can be as simple as just taking a piece of plastic and putting it in front of your converter. Neutrons then recoil off of hydrogen nuclei in the plastic, where those protons then go into the image plate and induce imaging. You can alternatively use, say, N2N reactions or other conversion reactions on high energy higher Z materials like either copper or iron or something else. And that can then produce beta or positron or X-ray or gamma ray radiation, which can then be used to induce imaging signal on the image plate. And this has been well demonstrated in the literature before. You can see a number of examples on the right here in which fast neutrons are used to do radiography of different metallic targets or different low Z targets using neutron to proton converters on image plates. Now, the actual imaging is based on the scattering kinematics of neutrons on protons, right? In the center here, we show the distribution of proton angles as compared to neutron angle relative to the normal for a converter placed on an image plate. And you can see these protons are generally forward directed. They're generally are directed in the same direction that the neutron was incident on the image plate, such that you get a true reflection of the actual image of the neutrons coming onto the image plate for the protons coming onto that. But there is, interestingly, if you look at the physics of the protons and where they're produced in the converter, you note that you would anticipate a trade-off between image sensitivity and image resolution based on converter thickness. The higher degree of converter thickness you have, well, that means you have a higher chance for neutrons to recoil off of hydrogen nuclei, which results in more conversion protons being produced, which results in higher sensitivity to lower fast neutron fluxes. However, this comes at a trade-off. For protons that are produced in the converter further away from the image plate, that proton scattered the same angle as a proton which is produced closer to the image plate will end up on the image plate at a position which is further away from where the neutron would have been directly incident on the image plate. Right? This proton that's produced further away, scattered at the same angle as this proton, ends up, assuming the proton travels in roughly a straight line, at a position which is further away from this central position, which is where the neutron would have ended up on the image plate. This results in a broadening of the response of the image plate to these fast neutrons, which results in an overall broadening of the proton signal on the image plate, which decreases image resolution. So there's a trade-off between this image spearing from protons, which sets a fundamental limit on the image resolution, with the sensitivity of the system. Now, in previous NIF experiments, they had, because they had not yet reached ignition, they had been focusing on just maximizing sensitivity, right? We just want to be as sensitive to our low neutron flux from our not igniting experiments. But now that NIF is in a regime where it is able to achieve ignition, we're interested not just in maximizing the total amount of signal, but in also maximizing the image resolution in order to improve the overall quality of our diagnostics. So there's interest then in analyzing and optimizing this conversion scheme based on this trade-off between image resolution and sensitivity. Now, in order to study this, we did some measurements of the impact of converter thickness at the University of Michigan using our P211 DT neutron generator. Now you can see on the left there the measurement scheme for this. The generator was wrapped in lead shielding was placed around the DT neutron generator in order to shield the intense burst of X-rays associated with the deuteron acceleration in the DT generator. A combination of lead and iron shielding was placed around converters placed on TR image plate foils, which were placed off to either side of the DT generator. Lead was placed around this converter and image plate scheme, with iron placed in the front there, and we'll talk about why that is in a second. But on the right there, you can see we 3D printed two converters in sort of a stair-step fashion, where the thickness of the converter was selected to span between the thinnest that was possible with the 3D printing systems available at University of Michigan, where the thickest section was selected to be a little bit greater than the range of 14.1 MeV protons in this plastic, where that range represents the maximum possible energy deposition of the maximum possible energy of the proton in the plastic, based on direct forward scattering of the 14.1 MeV neutron onto that proton. And you can see on the bottom there the read out images from these irradiations. And we'll talk about the readout system in a moment here. But you can see a greater degree of darkness on the image with increasing thickness of the converter, which is exactly what you'd expect, right? A higher degree of thickness, more signal, greater darkness on the image plate, and that's exactly what you observe. Now, the neutron generator we used for this, obviously we don't have access to NIF at the University of Michigan, so we need a surrogate for that. So we use a compact DT fusion generator manufactured by Thermo Fisher Scientific. This is based on acceleration of deuterons into a tritiated target, where that tritium is embedded in tungsten. The converter and image plates were placed off to the side at 90 degrees, as based on previous measurements of that. That's the region of highest neutron flux, which allows us to most easily make this measurement. And at this 90-degree position, you get the exact 14.1 MeV fusion neutron energy that you expect from NIF, which is good, as it allows us to make a one-to-one comparison between these measurements and similar ones at NIF. Now, for these measurements, we used Fujifilm TR image plates, where TR image plates were selected in order to minimize any energy loss of the protons in that mylar thin sheet. Additionally, like I mentioned, external light can cause fading of these image plates. So these were assembled as converter with image plate, and then the entire thing wrapped in aluminum foil with tape used to shield any holes in order to prevent light from being incident on the image plate, in order to just prevent any amount of fading while the experiments were going on. For the readout, we used a Typhoon FLA 7000 readout, which you can see pictured on the right here. This uses a 650 nanometer laser readout into a PMT in order to do the phosphorescent imaging. And then, like I mentioned, we just use a bright light between each measurement in order to clear the image plates before going and measuring with them again. And then the image J software was used for analysis. Now, ion shielding was selected over lead shielding in this context, where we want lead shielding in order to minimize any amount of environmental activation gamma rays from being incident on the image plate, since that just creates additional background. But the problem with that is that at these high energies, lead is actually a really effective fast neutron shield. On the left here, we show the total neutron cross section for lead compared to iron. And you can see that iron has a much lower fast neutron cross section, meaning that you reduce attenuation of the direct fast neutrons coming from the generator, which is the signal we're interested in and that we don't want to be attenuating. But iron is still a relatively effective X-ray and gamma ray shield, so we're still shielding most of the X-rays from the generator and gamma rays from room environment activation. Now, there is some concern that thermal neutron capture in iron could produce a high degree of background. But on the right here, we show results of Geant 4 simulation in which we look at the electron and proton energy deposition in an image plate for a corresponding measurement scheme. And I'll talk about in a moment this Geant 4 model. But you note that while the proton data, you can clearly distinguish the image plate in the center of the image, the electron data is uniform over the entire simulated region here, and is the entire image plate, and is relatively low in intensity compared to the proton signal produced in the image plate. So this means that the electron data, which corresponds to the gamma rays emitted from thermal neutron capture in iron, is both not that intense compared to the signal and can be easily subtracted off as uniform over the entire image plate. Now, measuring image resolution is relatively difficult, so we choose instead to use Geant 4 simulation in order to get an idea of the image resolution of this system. Now, on the top left here, you can see the Geant 4 model that was used here, in which we include the generator casing, as well as the front iron shielding, and then a model of the image plate with the converter put on the front of that. And these components were selected as these are the ones that are directly in the path of the fast neutrons headed to the converter and image plate. In order to calibrate the energy deposition that you're going to get out of simulation to the actual photostimulated luminescent signal intensity, which is the thing you measure when you go into a readout on an image plate, we use measurements of the proton to PSL, which were conducted and are demonstrated in the literature. These measurements were conducted using accelerators to put protons directly on image plates and then measure the light output signal that's gotten off of that. And you can see on the bottom left here the calibration function that we took from literature. On the right here, we show an example of a measurement in which we use simulation of the image resolution in which we use a region placed over half of this system, which just is set to kill neutrons that pass directly through it. This gives us a line spread function an edge spread function for neutrons that are not killed versus neutrons that are killed. And then if you take the first derivative of that, the full width half maximum is a common quick hand way to estimate the image resolution of this system. Now, I'll note here that, like I mentioned earlier, we're not simulating the full complete image resolution of a corresponding measurement. What we're doing is we're simulating the smearing of the image resolution caused by proton spread from the neutron to proton conversion. This is not a full description of the image resolution of the system, as that also depends on things like statistics of the measurement. But this proton image smearing sets a fundamental limit on the best possible image resolution that could be achieved. as well as other components like the image resolution of the image plate and the image resolution of the scanning system, but those are relatively a high resolution compared to this proton image smearing. So this sets a fundamental limit, which is of interest when designing these measurement systems. Now, looking at the result here, on the top right, we show the normalized signal intensity for both our measurement and simulation, in which we normalize that to the signal intensity at 4 millimeter thick converter. And you get exactly the result that you expect. You get increased signal intensity for both measurement and simulation with increased converter. Where that levels off at around 2 millimeters, as 2.5 millimeters is the range of 14 MeV protons in the plastic. We also get relatively good agreement between measurement and simulation, which provides some confidence in our simulation model and looking at things like the proton image smearing, which is shown on the bottom here. And again, you get a higher degree of image smearing with increased converter thickness up to, again, around 2 millimeters, which is where you reach the range of the protons. So any protons that are produced in more of the converter don't reach the image plate, so they have no effect on the image plate signal that you see either in measurement or simulation. So this optimization allows for the user to go and select a converter thickness that is most appropriate for their particular application, whether they need a higher image resolution or a higher degree of signal intensity, just depends on the particulars of their measurement. Now, one potential way to improve this beyond just using a plastic converter in an image plate is to use a filter. Now, a filter is a relatively high Z material which is placed in between the plastic converter and the image plate. And the idea is that this allows you to filter out undesirable protons. If we imagine two neutrons, which were both headed down orthogonal to the image plate, and then we imagine that each of them scattered off the hydrogen nucleus in the plastic converter, but they're two different angles. One at a relatively high angle and one at a relatively low angle, or by angle here, I mean the scattering angle. What we want is to use this low angle proton for the imaging, because it is more reflective of where that neutron would have ended up on the image plate. It gives you a more faithful idea of the neutron image, which decreases the degree of proton image smearing. The filter allows this proton to survive as, based on the scattering kinematics, this proton has more energy and it has a thinner path length through the filter, which means it's more probable that that proton will survive passing through the filter. However, this higher angle scattered proton has a lower energy and has a greater path length through the filter, which means it's more likely that the proton will be killed by the filter, which is what you want, right? You don't want to use that proton for your imaging, as that decreases it makes worse your image resolution. Now, on the right here, you can see an example of a simulation, not in Geon 4, but using a basic Monte Carlo model in which you fire protons in a beam and then assume they have a fixed range based on their energy through the scattering kinematics. And then you assume they travel through straight lines. And you can see here a 2D distribution of where protons deposit their energy, both in the converter in this bottom region below the red line and in the filter in this upper region. And you can see that with increased filter thickness, you get a cutting out of these protons that are at greater angles. So this results in a sharpening of the response of the image plate to neutrons incident in a pencil beam on the image plate, which decreases the image resolution, or improves the image resolution of the system. Now, this is anticipated to come at a trade-off. You lose this additional proton signal, which results in lower sensitivity. And simulating that, we simulated that for both a relatively low Z proton filter aluminum, low Z proton filter aluminum, as well as a high Z filter tungsten. And we simulated that for a number of different thicknesses. And you get exactly the trade-off that you anticipate, right? You get, with increasing thickness of filter, you get a relatively lower signal intensity, but a relatively improved degree of proton image smearing, right? You get a lower degree of smearing, which results in better image resolution. And we'll note that the best possible proton image smearing, which is at these sort of higher filter thicknesses, is better than the best possible image resolution that you can get using any of the tested converter thicknesses. And this could potentially be advantageous for really high neutron flux environments like NIF, where it's acceptable to have this high loss of the neutron signal. Um, so just to bring everything together as a conclusion, image plates are effective tools for radiation imaging. They're cost effective, they're relatively easy to use, and they're sensitive both to charged particles as well as to X-rays, which makes them useful for a high number of applications, whether that's medical X-ray imaging or accelerated diagnostics or neutron diagnostics for large fusion experiments like NEF. Additionally, we demonstrated both in simulation and in measurement the use of fast neutron to proton converters, where that's based on the scattering of fast neutrons off hydrogen nuclei and using the intrinsic charge particle sensitivity of these image plates in order to image the protons, which gets you an image of the neutrons. And there's a trade-off in image resolution and image signal intensity based on the thickness of converter that you use, up to, for DT neutrons, up to 2 millimeters, that being, again, the range of these 14 MeV protons. One additional possible option is the use of filters, which can enhance the number of options you have in this trade-off space by allowing you to have higher degrees of have lower amount of proton smearing based on using really thick filters at the cost of even lower sensitivity of the system to fast neutrons. Now, future work for this includes demonstration of filters in measurement applications to demonstrate what application spaces would be most useful for individual combinations, as well as just to prove this concept in measurement and to validate the simulations here. Additionally, we intend to do a full analysis of the different contributions of image resolution, how a loss of signal intensity contributes to lower image resolution, and how that represents an additional degree of trade-off in converter and filter thickness. And then we're also interested in going and using this technology in order to make measurements of the spot size for our DT generator that we use for these measurements, since that can have an impact on its utility as a fusion neutron imaging tool. For example, on the right here, we see simulations of using a DT neutron imager in order to do neutron radiography, in which we see the much greater sharpness you can achieve with a small fusion neutron spot size. So by imaging the spot size of our DT neutron generator, we can determine its applicability to do fast neutron radiography measurements. With that, I'd just like to thank our sponsors, particularly at the DOE and NSA, for funding this research work, as well as just the DOE NEUP grad fellowship program, as well as thank our collaborators both at Livermore at NIF and at the University of York. And then I'd like to thank you all for your listening and thank you all for your time, and I'm happy to take any questions. Thank you.
Nice job, Colton. Yeah, we have a couple questions here, so I'll just go over some in the time that we have left. One of the first questions that came up, so it's probably going to be relating to some of your earlier slides. They asked, why does the R value rely on the natural logs of attenuation?
Okay, can you hear
There
me?
you go. Yeah,
I'm so sorry about that. I bumped my computer and the screen closed and it kicked me out. I'm so sorry.
no worries. Do you want me to repeat the question?
Yes, please. I didn't hear it.
Yeah, so they asked, why does the R value rely on the natural logs of attenuation? So I'm guessing this is like slide 5 or 6. It was early
Yep.
on.
Yeah, so the natural log of attenuation gets you the mean free path of the neutrons and gamma rays based on the normal just Beer-Lambert exponential attenuation of the neutral charged current, or so the neutral particle current. So the R value is just defined as the difference in the mean free path for neutrons and gamma rays. You could more directly utilize the difference in intensity, but this is useful as it's more directly as you can directly take say values that are in the literature, which are typically based on mean free path lengths, which uses the ratio of the natural log. This allows you to directly compare that to literature values for different Z number materials.
Cool. Here's another question, which is actually one that I was going to ask if no one else asked it. And that's how many times, generally speaking, can you use or reuse imaging plates before they have to be disposed? And how would one determine if it's, still good to use?
Well, as far as I know, they're infinitely reusable. I have not heard of anyone having like a problem with, like a permanent imprint of something. Maybe if you exposed it to a really, really intense dose, you could cause enough crystal damage. Like if you put it directly in the path of a really, really high, really intense accelerator, you could like just burn the thing, and that would cause damage. But as far as like exposure damage, I haven't heard of that. The way to check it would be if you go and do the cleaning based on the really just putting it under a white light, if after doing that you're still seeing an image, then you probably have some issue with an image being imprinted on that. But that's not something that I've ever heard of.
Cool. Let's see. Another one is so like when you were describing the different types of imaging plates used, I think one of the ones mentioned was gadolinium. And so they're asking what other materials could be used. I think they're saying, for instance, what about like boric acid instead of gadolinium?
I know I know there are schemes using lithium. I think they use like a lithiated crystal, so that way you don't even have to dope it. You just directly use the lithium in there. I've never heard of anyone using boron. I think if, as I understand it, boron is typically very hard to load into things compared to lithium, based on my experience with organic scintillators. So I think that probably wouldn't be desirable. But I do know that lithium, as a thermal neutron modality is a thing. But gadolinium is preferred because of its higher capture cross section and its ease of loading.
Cool. Next up, we have so with the advent of digital radiography, what possible advantages do you think can still be offered by using imaging plates?
So like NIF has both modalities, right? They have a digital readout based on a CCD camera on a scintillator, but they still use image plates because that scintillator is very easy to overwhelm in the really high flux environment of NIF. So the image plate is still useful as a tool when doing really high flux shots. Additionally, image plates, they're cheap, they're easy to use, and the instrumentation for them is very simple, which makes them useful for field applications, and useful for in just really high flux environments where they have that high degree of linearity. You don't have pile up with an image plate like you would with a scintillator on a camera.
Cool. Next up is someone in the audience asked if you can talk a bit more about the quenching effects that you alluded to before.
Yeah, so I believe you all have probably talked about quenching in this summer school in the context of organic scintillators. This is a very similar effect. For the same amount of energy deposited, you get a lower light output for a heavy charged particle than you do for an electron or for an X-ray, which has its sensitivity based on electron either produced through photoelectric effect or through Compton recoil. And that's just due to the fact that a heavy charged particle causes crystal damage as it moves through the PSL layer of the image plate, which disrupts the crystal, which decreases the amount of these color centers that you can produce, which decreases the light output. Again, all exactly the same as how quenching works with organic scintillators. And this can just be measured based on the ratio of the light output for energy deposition, which is what was done in this publication here.
All right. Let's see. Here's one that just came in. Typically, how deep is the image recorded within the imaging plates, and how does this affect retrieval and fading?
That is an interesting question. The PSO layers are typically on the scale of tens of microns thick, up to 50 micron thick. It depends on what type of image plate. In that range, unless you use for the context of like electron and X-ray, it would be basically uniform because that thickness is really thin compared to the range of those particles in the material. In the context of heavy charged particles, that's not true. And that might be an interesting thing to study, would be how that affects that, and if that has some nonlinear effect on the quenching. I don't know of any literature that studies that problem. Um, I haven't read anything, so I think that would be an interesting research question.
Cool. All right. I'm
My
gonna.
guess, okay, actually, sorry, can I add on to
Yeah,
that?
go
My
ahead.
guess would be that it probably doesn't have a big effect, based on the fact that the laser light can be quite penetrating and could probably still read out no matter where the image is placed in the layer. So I would guess there's no effect, but I could not say for sure without measuring it. Sorry, I didn't mean to cut you off.
No worries. For this next question, I'm just gonna slightly rephrase it. So basically, like, what equations should someone keep in mind in terms of helping them understand or describe how the imaging plates work in terms of like their methodology?
Well, this one that's right on screen would be very useful. This is the underlying physics of the F center, the color center production in the image plate. And that's really all there is to it. I mean, if you're interested in doing image reconstruction, right, then you need to study other things like MLEM or other image reconstruction kernels and there's a number of good textbooks out there that you should go and read if you're interested in taking the image on the image plate and translating that into say neutron imaging using pinhole or coated aperture imaging. But as far as the actual image plate itself, it's just this physics that's going on here, based on the production of the color centers.
Cool. And like tangentially related, since we're on happen to be on this slide, one of the questions was just on why specifically europium's used as a dopant and whether other ones could be used. But I see here you're saying that chlorine and bromine could also be used, for
Well,
instance.
not as the dopant. That's just the halide in the other section of the crystal. I believe there are other image plates that use things other than europium dopant, but europium has the highest light output. The barium fluoride halide with europium, it has the best light output, and that's what's most commonly available in commercial image plates. And to my knowledge, there's no reason to use anything else. Maybe that's not true. There are other people that have done measurements in the literature with other dopants, but this is the one that has won out as time has gone on.
Cool. All right. And one just came in and they were wondering like how long does an image like remain on the plate before you have to like retrieve it?
Yeah, so for these measurements, we measured them in less than 10 minutes in order to just make sure that there was no fading. We sort of hustled from our Neutron lab down to the lab with the readout system. But the degree of fading is on the order of, again, tens to hundreds of minutes. So I would not leave it for more than a day without going doing the readout. I recall when we initially tested it, we had them for a day we just like left them and saw what happened, and there was still the image on there, but it was pretty faint. So I would do imaging on the order of at least an hour, at most like an hour after your measurement.
All right. We're getting close here to the end, but we still have a couple more things we can go over. One of the questions is back to the NIF as a concept, and they're questioning since NIF as a concept is being developed towards potential power plant or power generation, This would require a much higher cycling rate for shots, and presumably imaging would take a bit of time, to go from shot to shot. So how would one address that?
Well, from a diagnostics perspective, I think that the diagnostics is very useful for an experimental facility like NIF. But I think for like an application, you would not necessarily need to be doing diagnostics for every shot, right? You'd have some standardized laser control system and a standardized target fabrication system that would mean that you have a good idea of what's going on, so you don't need to be going and doing these diagnostics for every single shot. So I think that's the answer: is you really don't need to be doing that at, say, the high rep rate of a commercial production plant.
Cool. Another question relates to how you actually read in the plates and everything. You mentioned that you could use lasers either as a line or as a point. They were wondering whether the different methods would result in different like resolutions, basically.
Not to my knowledge. I think the difference is just the readout time. Just the line scan system doesn't require you to go and do that measurement. So each of them, I would think, fundamentally give you the same image resolution. There's different image resolutions for different, scanning systems, dependent just on the manufacturer and on the quality of them. But I don't think there's any fundamental difference in the image resolution between a point scan system and a line scan system.
Right, and last one before we close things off. Just generally speaking, are imaging plates affected by any environmental exposures or things that one would be concerned about?
So there is a higher degree of fading at higher temperatures, just because you get higher thermal recombination. There are also, a higher degree of fading when you expose them to light. You need to make sure that you're in a light tight environment. Otherwise, they're waterproof. At least the MS and SR ones are waterproof because of the mylar layer. TR not so much. Otherwise, I don't know of any particular, environmental effects beyond those.
Cool. And with that, we're just about gonna get on time. So again, thanks again, Colton, for the talk. I think people will be able to watch the lecture in the future via the links and everything. Otherwise, we'll see everyone tomorrow for the last lecture for this week on imaging. Thanks.
Thank you.